Hi, thank you for coming. Are people surprised to hear you're an engineer because you're a woman? Do people assume you're smart because you wear glasses? These are called biases, and turns out machines make the same mistakes as well. Apple's SEXIST credit card investigated by US regulator. Microsoft created a Twitter bot to learn from users. It quickly became a racist jerk. What I've just read are all real citations describing true stories or represent mistakes made by an accurate machine learning model. What does it mean, for example, that a model is 93% accurate? It means it succeeded to predict correctly 93% out of the test examples. But how? What data does the model use to make its decisions? Should it be using other features to make these predictions? I am Bitya, and today we're going to explore how machines make decisions. I'm a data scientist at Intel. I'm studying statistics at the Hebrew University of Jerusalem, and I love asking questions about data. So, back to our question about accuracy. What you see is an output of a model that accurately separates pictures of doctors and nurses. The woman at the top is a nurse, and at the bottom, a doctor. The model prediction is wrong for the doctor. Does high accuracy mean the model learned what we expect it to learn? Not at all. As you can see, the model was looking at the face of the person and the hairstyle to decide if the person is a nurse or a doctor. It mainly classified a man as a doctor and a woman as a nurse. The reason is that it had seen more examples of male doctors than female doctors, and the opposite is true for nurses. Here we can see an unbiased version. The prediction is based on the short sleeves for the nurse and a white coat plus stethoscope for the doctor. One of the most important questions a data scientist should ask about a model is what features have an influence on the prediction and how does each feature contribute to the decision made by the model. It is frequently a conflict whether to use a simple model such as logistic regression or decision tree or a complex algorithm such as deep neural network. This will be hard to infer, but reach far higher accuracy. If the model is simple, the model is the best explanation of itself. Otherwise, we would like to explain and infer the model predictions via feature importance, to be able to tell how much impact each feature has on the model's decision. But why? If the results of the model are good enough, who cares about explanations? Understanding why the model made a certain decision might have regulatory implications. For example, some decisions might be racist or sexist. Besides, the ability to provide explanations internally to ourselves, to the business team of our organization, and to our customers is critical. For example, if you want a doctor to use a model, the doctor must be able to infer the results, to explain the diagnosis to the patient. It will also help us as a data scientist to improve our model by eliminating irrelevant data and find biases in our data. An explanation can be either local, explains the contribution of each feature to the prediction of a single sample or instance in our data, or global, explain the contribution to model predictions of features across all instances. An explanation tool can be used to explain all models, or it can fit a specific group or family of models, for example, trees. SHAP, which stands for Shapley Additive Explanations, was proposed by Scott Landberg et al. In 2017. It is one of the most popular model-agnostic local technique that is used to explain predictions. The algorithm is based on Shapley values from the domain of game theory. Consider a group of players who won a prize. We now have a credit allocation problem. How much should each player get out of the total prize? What was the contribution of each player to the win? It is fair to distribute the prize according to individual contribution. In 1953, Lloyd Shapley suggested Shapley values as an optimal solution to the credit allocation problem. The solution satisfied three axioms known as the fairness axioms. Efficiency. The sum of prizes for each player is the total prize. Symmetry. If two players have the same contribution to the game, they get the same prize. And linearity. If two games are independent and we're considering it as one long game, then the prize for a player from the long game equals the sum of prizes for each game separately. Let's say Bob is a player. To determine Bob's contribution to the game, the outcome of each possible coalition of players should be compared to the same coalition without Bob. This process will give us the average marginal contribution of Bob across all possible coalitions, known as Bob's Shapley value. The analogy is straightforward. The game is our model, and the players are independent features. SHAP values explain the contribution of each feature to the difference between the average model prediction using no features and the actual prediction for a given instance. Here is an example of SHAP with a simplified version of the Kaggle Titanic dataset. Dr. Henry William is a randomly selected survivor, a single instance in the dataset. My simplified version of Titanic consists of 4 features: age, sex, class, and the number of relatives. In general, if we want to know the outcome of the model for each subgroup of features, we need to train a distinct prediction model using each subgroup of features, which means 2 by number of features models. For example, we would like to calculate the age SHAP value for Dr. Henry William. We start with the mean prediction, which is 0, not survived, because about 75% didn't survive. Now we are looking at combinations of one feature, and we train a model for age, class, sex, and relatives. The prediction for Dr. Henry William based on age only is 0, not survived. Then we continue to combinations of 2 features, which contain age. We train a distinct model for each combination and use it to predict whether Dr. Henry Williams survived or not. As you can see, the outcome of all models are not identical. The marginal distribution of age class, for example, is the difference between the prediction of the model we trained for age class minus the prediction of the model we trained for a class. The process continues to combinations of 3 features and finally, the full model. The SHAP value for age is the weighted average of all marginal contributions. This process is not scalable. It is exponential in the number of features. To solve it, Lambert suggested several approximation algorithms. I'll show a Python example of the kernel SHAP model agnostic approximation kernel explainer. In addition to the model agnostic version of SHAP, there are also multiple model-specific explanations algorithms, including Deep Explainer to explain deep learning models. So how can I use SHAP model with Python? The process starts as any standard machine learning task. I load the data, clean it, split it randomly to train and test, then I trained an XGBoost model with almost default parameters. Time to explain the predictions. First, I created the explainer object. The input of the explainer is the prediction function of the trained model, which will be used as a black box, and xtest, the reference distribution. The reference distribution is used to replace missing features in the full model instead of building a model for each subgroup of features. Then, I use the explainer to compute SHAP values for each feature for each instance in the dataset. SHAP has a variety of visuals. I will show my 2 favorites. What we can see here is the summary plot. For each feature, an instance is represented by a dot. The x-axis is the SHAP value. Each feature is colored by the range of its values from low in blue to high in red. The plot is sorted by the sum of SHAP values over all instances. It means that features are ordered in descending order by feature importance. Look at the sex feature. It is a binary feature. Here, blue represents the males and red represents the females. It is clear from this graph that if you are a woman, you have a much better chance to survive. Now, look at age. We can see young people have a better chance to survive than adults. but there is a range of ages in the middle that it looks like age is not a main factor. This is the plot for a single instance. It will help us understand the prediction for each instance. So, if we go back to dear Dr. Henry William, we already know that he survived, but the model predicted that he didn't survive. Why? Look at the graph. Probably because of his age and number of relatives. As you can see, we can use the model to get highly accurate predictions. It is important and interesting to be able to explain these predictions, especially when the predictions are not correct. Why did these predictions happen? Perhaps analyzing the answers to these questions will enable us to understand why we, as humans, make the biased decisions that we do. Thank you for watching. Feel free to contact me for questions or more information. Bye.